That was a yes, a tentative, suspicious yes. Go ahead.
Dear God, I thank you for this day. I just thank you for every student and just for this group of students, how every element just really has something to add. And I just pray that you'd be able to discuss how we learn a lot in my first name. Amen.
Amen. Strange. Prayer did not seem to have any, that prayer did not have any auxiliary comedic goals in mind as far as I could cipher. I feel like I may be losing touch. Let's see here. Okay, so I'm going to start today by talking about the classification of groups up to order 6. And this is going to be a little bit annoying because what it means is that your the blood, sweat, and tears that you poured into your homework to prove that something was isomorphic to a particular group of order 4, if you did that, it feels like you might have done that. Well, it could have been circumvented by this theorem. Okay, so first of all, I would point out if the group is of prime order, right? We proved class before last, or maybe last class, I forget, that a consequence of Lagrange's theorem is that groups of prime order are what? Cyclic, right? Yeah. And it's easy to prove that any two cyclic groups of the same order are isomorphic, right? If you don't believe me, here's the isomorphism. If I take a to the k and I map it to b to the k, this gives the isomorphism of this is isomorphic to that. And this isomorphism, of course, works in the finite or the infinite case, right? I slipped this into a previous lecture notes. You may or may not have noticed. Anyway, so of course, cyclic groups of the same order are isomorphic, all right? So up to isomorphism, if we have a group of prime order, for example, 1, 2, 3, or 5, let me give myself a little more room here. 5. Well, we already know that up to isomorphism, there's just, well, the stupid group. Here we've got Z2. Here you've got Z3. That's a cyclic group of order 3, right? And here we can use Z5. There's our typical cyclic group of order 5. All right? And so there you go. If you've got a group of order 2, up to isomorphism, it's Z2. All right? Now, how about 4? Let's talk about 4. 4 is not prime, of course, but what are the divisors of 4? 1, 2, and 4, yeah. So that means that the possible orders of elements of a group of order 4 are 1, 2, and 4, right? So if there exists A in G, and so let's suppose, I'm supposing what? The order of G is equal to 4 for a moment. So if the order of the group is 4, right? If there is an element of order 4, if there exists A and G with the order of A equals to 4, then G is isomorphic to Z4, right? It's a cyclic group of order 4. If it's got one element of order 4, that means it gives you the whole thing, right? Because to say it has an element of order 4 is to say that E, A squared, A cubed are distinct elements, right? Which is to say that the Cayley table looks like this, right? So the one possibility up to isomorphism is Z4, right? But there's actually two possibilities here. The other thing that could happen, right, is there could not exist, right? There does not exist A, an element of G with order 4. Then what has to happen? Well, you can't have everything with order 1, right? The identity is unique. To say that the element has order 1 is to say it's the identity. You can't have 4 identities. We proved that day 1 in here. There's just one identity. It's unique. So that means that what has to happen is the only possibilities are 1, 2, and 4, right? So if there's only one identity and you got 3 elements left, what do you have to say about those 3 elements? They all have to have order 2, right? So A, B, and C have to have elements. So this is the second possibility. Here's case 1. Here's case 2. So in case 2, you have 3 elements of order 2. A squared is E, B squared is E, C squared is E. Right? So, help me fill out the table. Think about it. What can I possibly put here? I heard C. Why can't I put B there? That would mean that, yeah, that would be a violation of having the distinct elements in each row, right? So that has to have a C here. What do I have to put here? B, yeah. What do I have to put here? A, right? This one has to be C. Process of elimination, this has to be B, and that has to be A. Now, just because I've satisfied the Latin square, right, that each row and each column has just one of each element in the group, doesn't necessarily mean that I've satisfied all the group axioms, right? It could be that we're not associative. The associativity test you can't see directly in the group. It's a little bit slipperier, you know? But what we could do, right, is you could look at U8, right? Here's a quick one to look at. U8, what's U8? It's got 1, 3, 5, and 7. 1, 3, 5, 7. You multiply that, what you got? 3 times 3 is 1. 5 times 5 is 1. 7 times 7 is 1. And this is 3. This is 5. This is 7. This is 3. This is 5. This is 7. Ooh, I did it wrong. Let's try that again. Let me erase the ones I'm not sure about. Let's see here. 5 times 3 is 15, which is what? 7. 3 times 7, 21, which is 5. Yeah, I think I can start using logic. Okay, that's 3. This has to be 3. This has to be 7. And this has to be 5. And you can easily see that this is the same pattern as that, right? Under the correspondence, 3 goes to A, 5 goes to B, 7 goes to C. I know that that's associative, right? So it follows then that this is associative through that correspondence, right? Now, what I would prefer to put here, though, is Z2 cross Z2. Or I suppose in Galilean's notation, Z2 plus Z2, like this. Which is what? Where addition is done modulo 2. It's easy to see, once I write that every non-zero element in that group has order 2, right? If you add any of the non-zero elements in Z2 plus Z2 to itself, you get back to 0. So this is called the Klein 4 group. Just to give it a name, this thing. And so there you go. Up to isomorphism, there's only 2 groups of order 4. The cyclic group of order 4 and the Klein 4 group. Anything else you write with order 4 is just one of these things in disguise. Order 6. In 6, you either have Z6 or you have S3. And you may have guessed where I'm going with this. That's going to be homework. You're going to show that if you have a group of order 6, it has to be one of those 2. You can argue much, and I'll try to give you a guided homework for this. I have a source to create the homework from, so I'll do that. But basically, the argument's going to be pretty similar. You're going to use Lagrange's theorem. If you have a group of order 6, what are the possible orders of elements? Yeah, 1, 2, 3, or 6, right? If there's an element of order 6, it's Z6, right? And then the thing that's going to be a little bit tough is to show that if there is an element of order 2, then there has to be, I mean, if it's not Z6, basically, it has to be S3 is the thing that's probably a little bit pickier to prove, all right? Anyway, that's it. Any question? So, yeah.
Clarify, our 6 and S3 not isomorphic.
Right. The things
Everything else is
yeah, everything every, my stupid table, if I have two, then these are distinct. All right, I'm just listing one representative example from each distinct isomorphism class. So now this is a great theorem now that we have it, right? If you have a group and you find it has order 4 and you want to prove it's isomorphic to the Klein 4 group, what do you have to do? But how do you do that? You show, right, you either show that there is not an element of order 4, or subgroup order 4 equivalently, or you could show that all 3 non-identity elements have order 2. That would show it's the Klein 4 group up to isomorphism. So this is very nice tabulation of results up to order 6. Okay, so with that, let me just tell you a few more things about normal subgroups. Oh no. Oh no. Oh no. So first, a fun bit of trivia. If N is a normal subgroup of G, and I'm going to start using, I should really have been doing that last class. I should put a little equals under it to allow the possibility, that allows the possibility that they're equal. All right, more on that in just a second here. If N is a normal subgroup of G, then the order, and here's an unfortunate place where we run into trouble with notation. The order of AN is equal to K, where K is smallest positive integer such that A to the K is an element of N. So here I'm actually talking about the order of the element AN in G mod N. Okay, that's different than the order of AN as a coset in G. These don't have to be equal. You're like, how can we use the same notation for two different things? I don't know, but we do. Apparently, there will not be confusion. So, there you go. So just to, here's a short explanation for why that's the case. What is AN to the power K? By definition, this is AN, right? AN, if you'll allow me this induction-free, kind of relaxed calculation here for a second. And so how does that go? Well, that's A to the K times N, right? What does it mean for this to be equal to the identity? What's the identity in G mod N? We talked about this last time, right? The identity in G mod N is precisely N, right? So to say that this raised to the power K gives me back the identity in the factor group is to say that A to the K is an element of N, right? And if you want K to be the order of AN, it should be the smallest K for which this happens, right? So what can you say about the order of a coset? It certainly can't be more than the order of its representative, right? Okay, so it has to divide the order of the representative, in fact. All right. Another thing I should mention to you is another point here too. For any G, fun. For any group G, we have 3 possibly distinct. There's more, I suppose, but these 3 stand out to me. Normal subgroups. So what are those? I would point out E, the set just containing the identity. The center, we talked about that before, right? The center of the group, the set of L elements which commute with all other elements. And G itself, these are all normal subgroups of G. Okay. You know, in terms of the only these two are possibly proper, right? These are proper subgroups. They could be proper. When would the center not be a proper subgroup? For example, when it's abelian, right? When it's abelian, z of g is just g. So it wouldn't be proper. Of course, E is a trivial subgroup. Okay, so those, some easy pickings. Those are examples of normal subgroups for any group. I should have mentioned that. What else should I tell you? Some low-hanging fruit here. The third point I would make, this is really easy, is that if H is, and we ran up against this in an example last time, but I just want to generalize that example. If H is a subgroup of G, right, and the index of H is 2, right? So what was the index? The number of cosets, right? Number of H cosets, I should say, to be more precise. So what's the deal here? If you have the identity times H, right, it's equal to H times the identity. That's just H. And what do we prove about cosets? They partition the group. So if there's just two cosets, if H is one of the cosets, what's the other coset have to be? Remaining left coset is what? In terms of set theoretic notation, it's just G with H removed, G minus H. Right? All the points except for the subgroup are the coset. Is it any different for the right coset? No. You have no freedom to make left and right cosets not match up, because you're stuck with the H being the identity coset in the left and the right case. And so all that remains is one more that has to match for the left and the right. So what's this mean? So therefore, H is a normal subgroup, because the left and the right cosets agree, right? They have to, by set theory. Now I mentioned this for A3 as a subgroup of S3, right? But now, if we know that the alternating group has half the order of the symmetric group of order n, you see that that argument scales, right? Because if the alternating group, if AN always has half as many elements as the symmetric group, that means that there are two cosets, right? Half are in the symmetric, half are in the alternating group, and the other half are the odd permutations, right? So there's two cosets, and that means that A sub n has to be a normal subgroup for any n. See? That's not a... So isn't that... I personally am very happy about this argument, because that means I don't have to look at n cycles and do some like sort of horrible, gory calculation to prove it. Think about proving all possible left and right cosets in AN match. Whoa. It's probably not that bad for reasons I don't appreciate because I haven't done it, but anyway. Okay. Anything else? Yes, one other thing. 4, a definition. G is said to be simple if there does not exist H, a normal subgroup of G, with H equals to E or H equals to G. Or, in other words, G is simple if it has no normal subgroups, no non-trivial proper subgroups. Normal, still haven't said it right. G is simple if it has no non-trivial normal proper subgroups. Proper normal subgroups. The point is you can't have a subgroup which is not G and is also normal unless it's the identity in a simple group. So can you guys tell me any simple groups? I got 4 of them on the board over there. There's a stupid one, the E, right? Any group of prime order is going to be simple, right? Example, G equals ZP, right? Because what are the subgroups of ZP? Does it have any subgroups? It does not, except for what? The whole group and the zero subgroup, right? So there are no subgroups, so it can't be, so it's simple. Yeah.
So are you saying that if there isn't an H as a G except for H?
Have I said it wrong? Here, let me try this again. Here, tell you what, let me try this again. H is simple, G is said to be simple if the only normal subgroups of G are E and G. There. Is that better? Yeah, I probably, follow man, whatever. All right, so any questions? So simple groups are something we want to understand more deeply as we go on in here. I would pause to point out that it is an annoying and sort of weird thing that we have given a technical meaning to the word simple. But there it is. Another example of a simple group actually is G is equal to the alternating group. Oh, what am I doing? Not double bar. The alternating group of order n for n greater than or equal to, what was it? 5 is simple. This I will not prove at the moment, but it actually turns out that plays a role in showing the insolvability of the quintic. All right, so that's part of that story I started with on day 1 that I won't complete in here, but I'll keep talking about. Okay, so there we go. So changing gears a bit. So this is just kind of some random trivia about normal subgroups that I need to talk to you guys about. If I have been coughing, if I had not been coughing last week, maybe I could have fit those wherever I was coughing. I could have said these things, perhaps. I don't know. There was enough time where I was coughing, right? Okay, so the natural homomorphism. Let's talk about the natural homomorphism. Here it is. If H is a normal subgroup of G, all right, then as we talked about last time, we can form the factor group by H, right? G mod H, set of cosets of G, right? How do we multiply things in here? Let me remind you. We had AH times BH. How do we define it? We proved this is well defined last time, right? We just multiply the representatives. And we proved that gives the set of cosets a group structure. This is called the factor group or the quotient group of G by H. Okay, so with this, there comes a natural homomorphism. We define, usually use a pi for this. Pi is a mapping from the group to the factor group, or quotient group if you prefer. And what's the mapping? It's just the natural mapping of x maps to the coset of x, or the coset containing x if you prefer. Right. To prove that this is a homomorphism, well, that's not hard, right? So how can we prove this is homomorphism? I mean, I'm calling it a homomorphism. That doesn't necessarily make it so, right? If I do pi of x times y, that's xy times h, right? By definition. So right here, this is the definition of pi. First of all, it's clearly going into the set of cosets, right? xh is a coset. That's fine. And this, by definition, is what? This is xh times yh. We proved that was well-defined last class. Given the normality of h, it's well-defined, right? Oh, but what's that? Pi of x, pi of y, there you have it. So this is the natural homomorphism, the assignment of the coset, right? Gives us a homomorphism. I need to prove a theorem for you guys now. I think I'll put it here. Yeah. Here's a theorem. If phi is a homomorphism from group 1 to group 2, then I get two things. One, I get that if, so I'm adding a condition here, if phi is a surjection, if, in other words, if it's onto, right? If phi is a surjection, and H1 is a normal subgroup of G1, then phi of H1, the image under the homomorphism of H1, is a normal subgroup of G2. And then 2, if we have a normal subgroup of the target space, G2, if H2 is a normal subgroup of G2, then the inverse image of H2 is a normal subgroup of G1. So we have no need of the surjectivity hypothesis for part 2 there. Excuse me. So let's prove it. Here we go. I'll start with 1. So what should we do? We should assume phi from G1 to G2 is a surjective homomorphism with H1 a normal subgroup of G1, right? So what's that mean? What's this condition mean? We put parentheses here. What that means for us to say H1 is a normal subgroup of G1 means that like G, H1, G inverse is a subset of G1. That's the most convenient criterion we have here for normality. Galian emphasizes the left and right cosets being equal, and that's useful for getting an idea of what the factor group mean, I mean how it works and all that, but as far as proofs actually go, it's much nicer to operate in terms of the conjugation. All right, so that's where I'm going to focus our attention proof-wise. So that's what we're given, right? We want to show that the image of H1 is a normal subgroup of G2, right? So what I want to do is I want to show that this is a subset. Well, I don't want to show that's a subset. What do I want to show? I want to say let's say Z be an element of, goodness gracious, I guess Y, phi of H1, Y inverse for what? For some Y in where? In G2, right? What do I want to do? I want to show that Z is an element of the image of H1. I want to show that Z is in phi of H1. If I can show that, that shows that the conjugation of the image of H1 is a subset of the image of H1, which is to say that the image of H1 under phi is a normal subgroup of G2. So what does it mean to say that Z is an element of this thing? It means that there exists some H in H1, right? Such that what? Z is equal to Y phi of H1, right? Or phi of H, I said. Sorry, just H. Phi of H, Y inverse. But why is the surjectivity important? I'll use onto to be friendly with you guys. Phi is onto, right? So what does that mean? So for Y in G2, there exists X in G1 such that what? Phi of X is equal to Y, right? So we can rewrite Y as the image of X, a particular point in G1. So let's put it all together. Z is equal to what? Z is equal to phi of X, right? Phi of H, phi of X inverse. Now what did we prove about homomorphisms? We proved that the inverse of the image is the image of the inverse. In other words, I can bring the inverse inside, right? It's one of the things we've proved about homomorphism in a previous lecture, is that I can bring that inverse inside, like so, right? And that wasn't something that wasn't a property of isomorphisms. I mean, it is a property of isomorphism, but it's also a property of homomorphisms. I don't need the bijectivity to do that. And then I use the homomorphism property, right? So this is phi of X, H, X inverse, right? Now, if I had been more clever, I should have, instead of writing G, I should have said, well, I don't know. You can just put X equal to G, right? Or put G equals to X, if you like. Why do I say that? Up here, right? Oh, I'm an idiot. Oh, goodness gracious. If the universe you're operating in is G1, is conjugation by an element of G1 still in G1 for a subgroup? Yeah, that's true for any subgroup, not just a normal subgroup. What do I need there for it to be normal? What I'm just about to underline in a different color. What should I have written there? This is not normality of H. 1. What should I have there? It is true it's equal to H1, but subset of H1 is what I'm after. Right. Remember, Theorem 9.1 said that it's sufficient to check that it's a subset. So that kind of cuts our work in half. I mean, it is true it's equal, but let's not work with that because that gives us twice as much work to do when we're checking normality. So, what's that say? That says that this is an element of what? It's an element of H1 because it's conjugation of something in H1 by something in G1. So, in total, this is then an element of phi of H1. So I've shown that an arbitrary point in the conjugation of the image of H1 by something in G2 is again in the image of H1. That is to say that Y phi of H1 Y inverse is a subset of phi of H1 for all Y in G2. And therefore, the image therefore, phi of H1 is a normal subgroup of G2 as we wanted. Excuse me. So there you go. There's the proof of 1. I didn't really do anything tricky there, did I? I just followed definitions, right? I used the homomorphism property. I used something we already worked out in the previous class. I really didn't do anything very snazzy here. How about 2? So I'll assume, again, assume phi is a homomorphism. That's interesting. And what else do I assume? And H2 is a normal subgroup of G2, right? Which means what? That means that, let's see here, Y, H2, Y inverse is a subset of H2 for all Y in G2, right? That's normality of H2. I want to show that the inverse image of H2 is a normal subgroup of G1, right? So what should I do? I should consider, let's say, X an element of G phi inverse of H2 G inverse. I would like to show, my goal is to show, in fact, that X is an element of the inverse image of H2. If I can show that, then that shows normality of the inverse image, like what I want. All right, so what now? What does it take to show that? Let's see here. Consider phi of X then. Let's calculate. What's phi of X equal to? Excuse me. First of all, but before I get to that, what does it mean to say it's in here? That means that X is equal to what? G, let's say, I don't know, I need some other letter. P. G inverse for some P in the inverse image of H2, right? There has to be some point in the inverse image which, when conjugated, gives you X, right? Before I calculate, I'm sorry, I'm an idiot. Note, what does it mean though? And what does it mean for P to be in the inverse image of H2? There exists, let's say, H in H2 such that what? Phi of P equals to what? Well, I mean, I'm sorry, this is dumb. Why don't I just say it more cleanly? What's that mean? This means that phi of P is what? More to the point. It means the image of P under phi is where? It's in H2, right? That's what it means to say that P is in the inverse image under H2 of phi. All right, now I've unraveled what that statement in light blue means. Let's try to use the homomorphism property to finish the deal here. So let's now I'll calculate. Keep in mind, I'm trying to show. What am I trying to show? My goal is to show that this is actually an element of phi inverse of H2, right? I don't want you to let me explode this because you don't want to write that. This is goal, right? Not something you should write in the proof. Writing that in the proof will make me think your logic is circular, and I will take off points. So just, you know that. Or soon you'll experience it. Let's see here. So phi of X is what? Phi of X is equal to phi of G, P, G inverse, right? Which is what? Phi of G, phi of P, phi of G, and I'll pull the inverse out this time, right? But what is this? So let's look at this. This is what? This is an H2, right? This is like, think of this as being the quote-unquote Y. Think of this over here as being the quote-unquote Y inverse, right? We know from the normality of H2 that this is an element of what? So I'm looking at y, something in H2, y inverse. This is again an element of H2 by the supposed normality of H2. So therefore, phi of x is an element of H2, which says that x is an element of the inverse image of H2. Consequently, what? Consequently, G phi inverse of H2, G is a subset of phi inverse of H2. And we conclude that the inverse image of H2 is a normal subgroup of G1. All right. So this is pretty awesome because there's a corollary here, right? Since E2 is a normal subgroup of G2, the homomorphism phi from G1 to G2 has kernel of phi, a normal subgroup of G1. We knew that the kernel of a homomorphism was a subgroup before, but we just learned something new. It's not just any kind of subgroup, it's a normal subgroup, which is really nice because that means we can form factor groups with respect to kernels. And now the main event. I'll do it over here. This brings us to what's known as the first isomorphism theorem. We have pretty much all the pieces, we just got to put them together now. Theorem: if phi from G1 to G2 is homomorphism, then let's see here, phi bar, which is a mapping, which is going to go from G1 mod the kernel of phi to the image under phi of G1, is an isomorphism. So I'm defining where, let's see, how does this work? Phi bar of x times the kernel of phi is equal to phi of x. This is how we define the induced isomorphism. So let's see here, what's left to prove? I hate to hurry through the proof of that. I'm going to put that off to next class. I'm going to show you a couple applications of it. How about that? Yeah, I think I'll do that. Proof isn't far from where we are, though. So, moments of indecision. Curses. Fine. No. I'm stuck in an endless loop. All right, I'm gonna knock myself out of this loop with some examples. I hate to not do the proof now because I got all this on the board, but oh well. So I have a couple vector group examples. These actually do fit into the first isomorphism discussion. So if we consider D4 mod the center of D4, and I know the center of D4 is a normal subgroup, then I'm going to be able to prove that this is isomorphic to Z2 cross Z2. Let me show you how. The Klein 4 group. So you guys know what D4 is, right? In our notation, 1x, x squared, x cubed, y, xy, x squared, y, x cubed, y. There's your 8 elements. The center is, again, 1 and x squared. I'm not going to prove that's normal here. Although I suppose I probably could prove that that's a normal subgroup. How would I do it? Just let phi from D4 to D4 be defined by what? How about this? Phi of x equals to x squared. I don't mean x. Z. Sorry, x means something here, right? So I can't use it as a variable. What's the kernel of that map? Oh, that's everything. I'm sorry, that's not what I want. Why am I doing this? I don't want to do this. I'm an idiot. I'm an idiot. Sorry, follow my notes. Let's call this thing n. And then xn is xx cubed. Yn is yx squared. And xy times n is xy and x cubed y. What happens when we multiply xn times xn? We get x squared times n, right? Which is just equal to n again. What happens when you multiply yn times yn? It's n again. What happens when you multiply xy times n, xyn times xyn? Its product of these cosets is again what? We get xy squared, right? Which is again n. So what does this show? 3 elements of order 2. Right? So it follows by our discussion at the start of today that this is a group of order 4, because you got 4 cosets and 3 elements of order 2, so it has to be isomorphic to the Klein 4 group. Another example, we could look at D4, oh no, not D4. Sorry, wrong example. Just 2 simple, nice examples. We can look at G equal to Z4, direct sum Z4. And you can either look at H, N equal to, let's say 0, 0, 0, 2, 2, 0, 2, 2, all right? And then G mod n is n, 1, 0 plus n, 0, 1 plus n, 1, 1 plus n, right? Versus, say, k, 0, 0, 1, 0, 2, 0, 3, 0, and you get g mod k equal to k 0, 1 plus k, 0, 2 plus k, 0, 3 plus k. So here's a group. It's got order 8, I think, right? And order 8, is that right? Maybe order 16, yeah. And so the two different factor groups. Can you guys tell me these are both order 4? Which one's Z4? Which one's the Klein 4 group? I mean, I'm telling you that they're distinct. Oh man, so many more things to tell you. But this is it for today. So this guy, right? Check it out. The order of all 3 of these is what? Order 2. Why? Because if you take 1, 0 plus n plus 1, 0 plus n, what do you get? You get 2, 0 plus n, which is equal to n again, because that's in n. So those have order 2. Every one of those has order 2, because if you add it to itself, you get something in n. So those all have order 2. 3 elements of order 2, Klein 4 group. This guy down here, you can check, for example, that 1, 0 plus k has order 4. If there's an element of order 4, it's a group of order 4. That's a cyclic group of order 4. So there's a couple of examples for you. Anyway, I have much more to say about the story next time. Thanks, guys.